Ideal gas law. We can take these laws, the Boyle's law, Charles' law, and Avogadro's, and we can put them all together into one single law. It's called the ideal gas law. And we could prove that mathematically, but I don't think most of you are interested. So here it is. PV equals nRT. Some students remember this by saying PivNert. But this is a really important equation to remember. We've encountered pressure and volume, and N was moles of gas, and T was temperature. What unit? Kelvins. Got to use kelvins for the temperature. And then there's this new thing, R. R is a constant. It's called the ideal gas constant. And it's 0.0821 liter atmospheres per mole Kelvin. If we're going to use the ideal gas constant, the ideal gas law with this constant, then we have to use the units that are in this constant. This is a wacky set of units, isn't it? Liter times atmospheres divided by moles times Kelvin. But that tells us what units to use for everything else. So pressure has to be in atmospheres, volume has to be in liters, amount of gas in moles, and temperature in kelvins. The ideal gas law can be used to calculate a missing variable for a gas that is not changing conditions. All the other laws we've talked about were if you change this, what happens to that? This will tell us, okay, we've got this sample under these conditions, how many moles of gas are in it? This is a slide showing all the different combinations between these relationships. May or may not be interesting. There's another law, Gay-Lussac's law, that we didn't talk about, but it's just, that's the relationship between pressure and temperature. So how do we use the ideal gas law? Well, let's do a problem to illustrate that. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. We read through the problem. What is the next step that we've been doing? Making a table. So let's do that again. We just, follow the pattern. 0.845 moles. And what letter do we associate with moles? That's N. The next number we encounter is 1.37 atmospheres, and that is pressure, capital P. And then 315 Kelvin, and that's a temperature, capital T. And how thoughtful of them. They put it in Kelvin. We don't have to convert it. Look what happened. We used up all the numbers that were given to us. We put them in our table, and we only have one row. There's nothing down here. That's because nothing's changing. In all of the other laws, all the other problems we did, something was changing. The pressure was changing, the volume was changing, something was changing. Here, nothing's changing. So as it turns out, we don't need that second row. Did it hurt that we drew it and ended up not needing it? Not really, no. We still have our numbers all organized. When you make the table and there's only one row, then it's the ideal gas law. PV equals nRT. See, this equation has no ones and twos, does it? It's just the variables. What is the question asking for? The volume. Calculate the volume. So we're trying to find V. This equation's nice. It doesn't have any fractions in it. So we'll just rearrange it to solve for V. We want to get rid of the P that is over there. So we divide by P on that side. We divide by P on this side. So we have the volume is equal to nRT over P. Well, then we do need to know what that R is, right? After a while, you'll probably end up memorizing it. It's 0.0821. The units are important. Liter, atmospheres, per mole, Kelvin. So to save ourselves a little grief, it's always a good idea to look at these units and check the units of the quantities you've got here. N is in moles, check. Pressure is in atmospheres, check. Temperature is in Kelvin, check. What do we do if one of them is not? You convert it. It's easier to convert it before you stick it into the equation. If our pressure was given to us in torr, then we would need to do a little calculation and convert it to atmospheres. If the moles, instead we were given grams, we'd have to use the molar mass and convert to grams. I'm sorry, from grams to moles. But this one's nice. So then we're going to take these numbers and put them in. N is 0.845 moles. R, it's tempting to leave out those messy units, but don't do it. Liter, atmospheres, or mole, Kelvin. Temperature, 315 Kelvin. All of that divided by 1.37 atmospheres. Now look what happens with the units. Moles cancel moles. Kelvin cancels Kelvin. Atmosphere cancels atmospheres. We're left with liters, which is a great unit for volume. So we get out our calculator. We have 0.845 times 0.0821 times 315 divided by 1.37 equals. So this equals, let's see, I've got 3 sig figs in everything, so I'll round this to 3 sig figs. 15.95 is going to round to 16.0. The unit is liters. That is the volume of the gas. Questions? I think in some ways the ideal gas law calculations are easier because you don't have the ones and twos. So there's less confusing things to keep track of. We can use the ideal gas law to determine the molar mass of a gas. It's hard to measure the number of moles of something. But for a gas, PV equals nRT. Let's write that down. PV equals nRT. Like if you have a solid sample, how do you measure the number of moles if you don't know what the substance is? It's pretty hard. If you have a gas, though, you can find N if you know the pressure of the gas, the volume of the gas, and the temperature of the gas. And that's why so much of this early work was done with gases. So let's look at this question. A sample of gas has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees Celsius and a pressure of 886 torr. Find the molar mass of the gas. The molar mass of the gas is not in that equation. Well, let's think about it. What is the molar mass? It's the mass of a sample divided by the number of moles, right? Molar mass, we'll call it capital M, is mass divided by number of moles, right? Because it's the mass of 1 mole. So if your sample is not 1 mole, maybe it's 5 moles, you'll take the mass, divide by the 5 moles, and you'll get the mass per 1 mole. So this tells us what we need to find. We need the mass of this sample, and we need the number of moles. Well, here they gave us the mass. Can we calculate the number of moles? We can, using the ideal gas law, right? So let's look at these. 224 milliliters. You want to do the table thing still? Just be consistent. So let's make a table, and we'll write down our numbers. I love things that you can just like use all the time. So 38.8 milligrams, that's the mass. That's not part of our gas law calculation. So I'm going to leave that out. 224 milliliters. Milliliter is a unit of volume. 55 degrees Celsius is temperature, right? What do we need to do to that? Change it to Kelvin. Do it right away. So 55 plus 273, that's 328. 328 Kelvin. 886 torr. Actually, I don't need to. 886 torr. That is what? That's the pressure. So again, we've just got the one row. So that's our big hint that this is going to be ideal gas law. PV equals nRT. For the molar mass, we have M divided by N. We need to find N. We need to find N. So let's rearrange our equation. So N has RT next to it. We need to divide by R and T. And if we do it on one side, we have to do it on the other side. So N is going to be equal to the pressure times the volume divided by R times the temperature. R equals 0.0821 liter atmospheres per mole Kelvin. Let's look at those units before we start plugging numbers in. Is our volume in liters? Nope. Let's fix it. So how do we convert milliliters to liters? Well, 224 milliliters, we're going to multiply by liters and divide by milliliters. What does milli mean? 10 to the minus 3. Milli, I can't point down there. Milli's on the bottom, so we put what it means on the top. And we end up with 0.224 liters. Use your brain when you do these conversions. Do you know how big a milliliter is? Can you imagine roughly how big a milliliter is? It's little, right? Think of that 10 mil graduated cylinder, 1/10 of that. It's a small. How big is a liter? It's a lot bigger, isn't it? So you don't want to take 224 milliliters and end up with 2,240 liters, because that's moving in the wrong direction. So we're not really using this second column as a second set of conditions, but we can use it to write down our converted values. So 0.224 liters. The kelvins are fine. What about the pressure? We need to put it into atmospheres. So 886 torr times, we're going to put torr on the bottom and atmospheres on top. We go to the table, or this is one that would be good to remember. 1 atmosphere, 760 torr. So we've got 886 divided by 760. So 1.17 atmospheres. Now we fixed the units, so we can just plug those into the equation and everything will be hunky-dory. Pressure, 1.17 atmospheres. Volume, 0.224 liters. R, 0.0821 liter atmospheres per mole Kelvin. Temperature, 328 Kelvin. Be careful when you do this on your calculator because there's two numbers in the denominator. If you want to multiply the 0.0821 times 328, then you have to put parentheses around them. So get your calculator out if you don't already have it out, and do this with me and make sure you come up with the same answer. So I've got 1.17 times 0.224 divided by 0.0821 divided by 328. So I come up with a number of moles that is equal to 0.00973. Or you could put that in scientific notation. Is that the answer to the question? Nope. Question wants molar mass. We need the mass divided by the number of moles. Well, here's the mass. I'm going to write up here, so I ran out of room. 38.8 milligrams, and we're going to divide by the number of moles, 0.00973 moles. What unit are we going to get grams per mole out of that? We're going to milligrams. So we need to convert the milligrams. Now, if you're thinking ahead, you could do that before you stick it in here, or you can do it after. We want milligrams to cancel out, so we're going to divide by milligrams, multiply by grams. We ask ourselves, what does milli mean? 10 to the minus 3. We have milli in the denominator, so we want to put what it means in the numerator. So we get 38.8 divided by 0.009, that wasn't a 9, 973 times 1 times 10 to the minus third. So I end up with a molar mass of 3.99 grams per mole. Anybody else come up with that number? Is it possible to have a substance with a molar mass of 4 grams per mole? Oh, helium has a molar mass of 4. I bet that's helium in there. What if your number came out as 0.4? Could anything have a molar mass of 0.4? No, because hydrogen is the smallest element. It has a molar mass of 1 gram per mole. You can't have anything smaller than that. If you end up with something that has a mass of 4,000 grams per mole, that's pretty far-fetched, especially for that to be a gas at these temperatures. Questions about this one? Yes?
So, we only did the gas law for the second row, why? Is it just because we converted it and we're using it?
Yeah, what we did, the question is, we just did it for the second row and not for the first row. What we were doing is, we didn't end up really needing the table because nothing was changing. And so these are our values. I had drawn the table, and so I just made use of it to put our converted numbers in there so that we could see what they were more easily.
Okay.
Yeah. Any other questions? You don't have to use a table for this. You could just label them and say, okay, the volume is this, and the temperature is that, and oh, I need to convert it, so I'll convert it, and there's other ways to do it. But with these gas, you can always start out with a table and fill it in, and then you may find that you didn't actually need the table, but it's still helpful because you've got your units and your variables all lined up. So gas behavior depends on conditions, and we said that the kinetic molecular theory of gases, there are some situations under which it doesn't apply. So we're just going to mention some of those. This is what we call ideal gas conditions, and this is where the gases follow the behavior predicted by the equations. This is at relatively high temperature and relatively low pressure. And so here there is a lot of space between the molecules. The volume of the particles is very insignificant compared to the volume of the entire gas. Because there's so much space and the particles are moving rapidly, there are no significant interactions between the molecules. Now, if we go to a lower temperature, where the gas is getting close to condensing into a liquid, when we squeeze it with a lot of pressure and cause them to get very close together, then we start to have some problems. Because now the interactions between these particles do become significant. The particles are moving faster and they're closer together. It's hard for people to interact if they don't even get close enough to notice each other. On a family vacation, we drove through Wyoming. Wyoming's a beautiful state, but it's a relatively large state. And the population is about the same as Fresno without Clovis, about 400,000 people in the whole state. And you see that when you're driving through at night. You can drive for miles and not even see a farm light. I mean, most of it is just completely empty. So that's a little bit like a gas, where the volume of the people is completely insignificant relative to the volume of the entire state, right? And if you spread the people out uniformly throughout the state, would there be much interaction between people? No, because you're not even going to be within shouting distance. So essentially, you're all by yourself, right? You're acting independently. Well, when you crowd those people into a smaller space, they're going to be running into each other more often. They're going to see each other. There will be some interactions, and that's what happens with gases too. The particles have to be moving a little bit slower so that then when they bounce into each other, they don't just fly off so fast that those interactions don't have any chance to take hold. And they also have to interact more frequently. So when we get low temperature, high pressure, then the ideal gas law just doesn't work so well anymore.